Hello, and welcome to another Math with Taebyn. My name is Taebyn, I'm a pup, bark bark, and so I would like to share some more math with you. This particular episode, I want to talk about eigenvalues and eigenvectors in linear algebra, and in particular, the geometry of what's going on. I'm going to assume you know how to compute eigenvalues and eigenvectors and basics of complex numbers. A lot of people can just compute them, but I don't know if a lot of people really understand what's happening geometrically. And it can be very useful to understand what's happening geometrically because it can help you actually do computations without doing the computations, if that makes any sense. I'm going to have an example of that in part 2. Anyway, so just to recall what the definition of an eigenvalue and eigenvector are, B is an eigenvector of a matrix or linear transformation, but I'll just say linear transformation for right now, of linear transformation T, which will be between two Euclidean spaces, corresponding to the eigenvalue. I'm abbreviating because that's a long word. Eigenvector, eigenvalue, lambda, if T of V equals lambda V. Right, so hopefully that you recognize the definition, and you've computed with this before and been able to actually compute these. But let's look at geometrically. What does this say? If lambda is a real number, so I use this notation, is in the set of real numbers, then notice what's happening. If I have a vector v, if I have this scenario, if I have a vector v, on the one hand, what does multiplying a vector by a real number do? It stretches it out, or deflects it, or shrinks it. So then maybe you're stretching it out when you multiply. Stretch. Or you might be reflecting it, right? If you multiply by a negative number, you're reflecting it over. Or you could be shrinking, something like that. And in any case, you end up on the same line through your original vector. Now, this equation is saying that when you do this, that's the same thing as doing what your transformation is doing. So what's happening geometrically is, for this particular vector that corresponds to this eigenvalue, you're stretching it out or you're reversing directions or whatever. So that's really nice geometrically. Let's look at a quick example. Transformation. Let's just go between two dimensions, I guess. By T of V equals 3V. So we're just going to define it that way. Then your transformation is tripling the length of any vector. Now, if in particular it's just an eigenvector, then you're only tripling the length of that one vector. So here's my vector, and then triple the length. So that's going to be, say, out to here. Example, suppose lambda equals -2 is an eigenvalue of your linear transformation corresponding to some vector. We'll just call it V. Well, then in that case, that means that, just by definition, that means that T of V equals -2V. Then what's happening there? And so this is saying you computed your eigenvalues and eigenvectors, and maybe you got that this is an eigenvalue corresponding to some eigenvector. Then what's happening is, for this vector and this vector only, well, not only any scalar multiple of it, but basically just this vector, you're reversing the direction as of the negative, and then you're doubling the length. So for that vector, what's your linear transformation doing? You're reflecting it over, flipping it over, and doubling the length. So for real eigenvalues, it's kind of a really nice situation. but we have complex numbers. So what about complex numbers? What about complex eigenvalues? That's a great question. So what about complex numbers? Well, let's say, what if your lambda was in the set of complex numbers? So I'll change this R to not an ocean, but a sea. That was stupid, but I did it. C, complex numbers. Now, if you remember things about complex numbers, any complex number can be written in polar form. And again, if you know about complex numbers, multiplying by complex number in polar form rotates the vector that you're multiplying by the angle theta. So this rotates vectors. And if you're multiplying by this r, you might stretch it out, but we're looking at rotating vectors by theta. For example, here's a matrix. Now, I've been talking about linear transformations. I mentioned that, and you might already know from experience that computing, like the eigenvectors and eigenvalues definitions, is the same basically for transformations as for matrices. If you remember or know about matrix representations of linear transformations, that's the whole reason they're the same. I don't want to talk about matrix representations in this video because that's a whole separate video. So, again, computing eigenvectors and eigenvalues, if you were to compute these, you will get that. The eigenvalues you get if you compute are plus or minus I. That's the imaginary unit. Not me, but I. If you remember, again, complex number stuff, this can be written in polar form as e to the I times pi over 2. Just a quick little reminder about why that is. It's because e to the I theta equals cosine theta plus I sine theta. But in any case, so you compute this, and it corresponds to some eigenvector. So what are we doing? If your transformation then, so let's say this, I'm not worried about exactly what the vector is. I just want to show you that multiplying by this matrix, what it does to this particular vector is that it, well, I'll just use the positive one, positive I. That's not the number 4. It's IV. Okay. That's the same thing as rotating by pi over 2. Rotates that particular vector by pi over 2, which, if you remember, that's 90 degrees. So whatever this vector is, which you can compute it, and you can see that this works. Here's the vector, and you're rotating counterclockwise by 90 degrees. And that's very cool and interesting. And there it is. And this, I'm doing this in 2 dimensions, but this is true in all dimensions. And so this is great. This is fun and very useful. Now, this, as I said, is part 1 of the video. In part 2, make sure to watch part 2 because I'll do an example in 3 dimensions where we use the geometry of the situation to find the eigenvalues and eigenvectors without computing by definition. And that's really fun and useful and really neat. So see you in the next one. Till then, more fun.